So thanks, Mehmet. So he has already described what we're going to do, and it is basically to fill a buffer, a 2D buffer, with the initial conditions of our heat equation. So over the next 1.5 days, we will try and do a simulation of a heat equation, and for now, we will fill in only the initial conditions. So to do this, of course, we need to access elements inside the buffer, and to do this, we need to somehow access arbitrary positions. So let's start with our hands-on session. So everyone can please go into day one fill buffer. So again, this is inside your source directory, Alpaca workshop slides, day one, and then there you have it, one fill buffer. You can see in the README what you need to do. We need to edit the initialize buffer kernel. This is basically a kernel which is going to fill in our buffer. And then we have to deal with pointers, the favorite thing of every C programmer, and calculate indexes of elements in our buffer. What we don't have to do, and what is already being done in this example, is to map elements to threads or to make a work division. All of this is already handled, and currently we only focus on writing the kernel which will fill the buffer. So you can do this, go inside the source directory and open initialize buffer kernel. Over here, you will find the solution for the last hands-on. This is what we expect. You will have something similar to this. Of course, we can remove all of this. So what I need is to fill a buffer with the value of the analytical solution. Okay, so what is the analytical solution? Well, we have it in a file aptly named analytical solution. It's inside the source folder, and I can show you what it has. So over here, you can find Alpaca function ACC. So a function which will be executed inside a kernel. And this is the analytical solution for our heat equation example for position x, y at time t. And you can see it is using some Alpaca math functions. We don't use standard library functions because this function can be used in a wide variety of accelerators. So maybe it might be used on a CUDA GPU or an AMD GPU. And then you want to use vendor-specific math functions. So Alpaca handles all of this mapping internally. So you can simply use the Alpaca math functions, and these will work optimally for you everywhere. So we have already defined this analytical solution. And you can see there's also a version for the host side, so on the CPU side. But you don't have to care about this right now. So what we need to do is fill in the analytical solution into a buffer. You can see we have already passed in the buffer, buff data, to our kernel, initialize buffer kernel. So ideally, what I want to do is write something like this. This is absolutely incorrect. I'm just trying to demonstrate what the idea is. So buff data, maybe at position 1, 2 should be, oopsie. So what I want is to do something like this, is equal to, I am now using And English layout and struggling equally. Yes. So buff data is something like, and I will fill it with my analytical solution.
What is the unit of x and y? Is it in cells? Is it in meters? Or
So the unit of x and y is in physical units. So exactly to map to physical units, so for example meters, we have already passed in two variables, dx and dy. So again, the question was, what are these x and y? Is this in meters? Is it in, what is it?
cells?
Cells? So the answer is, it is in physical meters, physical units. And we provide dx and dy. And these are what you can use to map from a thread index to a physical position. So I can show you, it would be like x position of thread multiplied by dx. So this is what we need to do. Obviously, this has a few problems. We need to still get the x position. The ACC, we always have. This is automatically passed to your kernel. You don't have to worry about this. We need to get y, similarly to x. To dy. And because we are filling in the initial conditions, it is at time 0, so we can simply put 0. The next problem we have is, aside from getting the x position in thread and y position thread, is accessing the correct elements in buff data. Obviously, I want this to look like careful of the positioning. So what I want is something like this. I want to access y comma x in buff data. So first of all, maybe let's try to fill in what these x position thread and y position thread should be. Can anyone take a guess? So what I'm trying to do is fill in data 5,2, for example, and this is supposed to be filled in by a corresponding thread. So over here you can see that thread 0,0 is filling in the 0, 0 index and so on. So to fill in an arbitrary position, what we need is the thread index. How do we get the thread index, the global thread index? Anyone in this room?
Yes. To which cell is the data pointing? What is the origin in your image if you go back to your image?
In the image? So the origin is correctly set.
Which cell? To the boundary?
No, it is set here to the boundary. 0, 0 is this one. And we are filling this complete buffer. So thread 0, 0 will fill this, 0, 1 will fill this one, 0, 2, and so on. So how do you get an arbitrary thread index? Come on, you can do this. The answer is already on line 41. Absolutely correct. Grid thread index. So this is what I need. I can remove all of this. And now I want something like this.
Use naming.
We have fans of the naming, so we can use that as well. Oh. So, okay, this is all well and good. I can fill in my buffer like this if only I could access my buffer like this. The good news is you can, but only if you're using MDSpan. And this is something we will come to later. MDSpan is the C++ way to handle pointers and pitches so that you don't have to do all this ugly pointer arithmetic that we were talking about earlier. But for now, because it is important to understand how data is stored and what problems you could run into, we are going to write our own helper, which is going to help us access the correct point in our buffer. So over here, you can see that buff data is a pointer to a double. And you can go into the helpers.hpp file. Over here, we have set up a function called getElementPointer. It accepts a pointer of type t, pointer to a type t, and it takes in a alpaca vector holding an index and a pitch. So just to show everyone again, so the index over here would be 5,2, and the pitch would be the row pitch, for example, is 32 bytes. The column pitch would be 3 bytes. So this is the pitch, and the index, obviously the original pointer is pointing to your origin over here. So what you need to do is now some pointer arithmetic. So I will write this alongside you. Hopefully everyone is following along. So how do you do this? Does anyone know what will happen if I do something like pointer plus 1? What does this do? I have a pointer to a type t and I add 1 to it. It will move one position in memory, and this is sort of important to know. One position in memory means it is jumping not 1 byte, but the size of t bytes. So it will go to the next t element because this pointer is pointing to t's. So what we need to do is also, when we are looking at pointers to t's and pitches, convert to the size of a single byte, because pitches are always in alpaca given in bytes, not in any other data type. So it's simply a byte. So first we will do a reinterpret cast. Okay, there you have it. And now what is happening is you convert your pointer to a byte pointer, and now when you add 1, you are moving ahead by 1 position in memory, which is just 1 byte. Next, okay, I want to get the pointer for the element at index idx given pitches. So how do we do this? What would be the mathematical way to do it? Can anyone help me out? I already have the origin, which is my pointer, ptr, and now I want to access index. So if I want to access this point, which is idx 0, idx 1, how do I do this? What do I need? This is ptr. What you need basically is this size which is pitch, and then you multiply the pitch by your index, and you reach it.
Index y, index dot y, bracket close, or index dot x. I guess it's probably index y.
So let's start out simple. If you wanted to get to the absolutely next element, what would you do? Just so what you would have done is pointer plus one, but now you've casted yourself into bytes. So how do you get to the next element?
Used by the page, but by the column page.
Exactly. You multiply by the column pitch. And the column pitch is nothing else but the size of t. So to get to really the next element, all you need to do is 1 into column pitch. So pitch. 0 or 1? 1. Because this is the fast moving index. So you are correct. Oh, thanks. So to access an arbitrary index IDX, what do you need to do? Basically, all you need to do is say, hey, give me IDX 1 multiplied by pitch 1 and IDX 0 multiplied by pitch 0. And that's almost it. So what this gives us now is, okay, you jumped over index 0 times this size, you jumped over index 1 times element size. Very nice, but you're still looking at byte pointers. If you return this, you will get a pointer to a single byte. What you want is to have a pointer to a type t. So what's finally left is to cast it back, reinterpret, cast. So you, yes, yes, also correct. Thank you. So I was missing the stars because obviously I want to cast to a pointer to a type. So there you have it. Cast all of this back to a pointer to a t, and I can just return this.
Can you please explain again why you need to make the asterisk for the type or byte and for t?
So currently you have a pointer which is an address, and if you cast it to a double, it will become a huge number. What you want to do is cast it to a pointer to a double. So it's still a pointer. So the address is the same. You're only saying that, hey, okay, now this address is pointing to a double. Earlier it was pointing to a byte, and now it points to an arbitrary t. Yes.
What is the advantage of having this double reinterpret cast versus just dividing pitch 0, so the slow moving, by the size of t?
So the question is, why don't we simply divide the slow moving pitch 0, by the size of t? And the answer is, well, that would be nice if it were divisible. So for example, over here, you can see if I have a data size of 3, weird, but okay, it can happen. And a padding of 11 bytes or a pitch of 32 bytes, you cannot divide it anymore. I mean, you can divide it, but then you will have a rounding error and then you will access incorrect elements. So this is why you first cast it to a byte pointer, a car pointer, whatever, and then recast it into your original data type.
Sorry, I didn't understand. What does pitch for brackets 1 and pitch
Hmm?
brackets 0 represent?
So pitch in pitch 0 is really this whole row pitch, the 32 bytes. It's the pitch in bytes to get to the next element. If you maybe we should talk in x and y's because it's easier. So 0 corresponds to y. So in y direction, if you wanted to get to the next element, pitch y represents the number of bytes you have to jump over. I hope.
The distance in memory as opposed to the distance in indexing, which is different due to padding.
So the distance in memory in bytes to the next element in that direction. Similarly, pitch 1 or pitch x is the distance in memory in bytes to get to the next element in x. So basically, literally the next element.
Actually, only pitch would be enough because data size is already known in the kernel.
Yeah.
I think only the raw pitch or pitch 0 would be okay, and it may be easier to understand.
What is the difference between size of t and the pitch in the x large?
So the question is, what's the difference between size of t and the x direction pitch? The answer is nothing. They're exactly the same. I think it's quite convenient to keep the pitches together like this. Yes, Rene.
If you go back to your editor
Mm-hmm.
and you reformulate your equation now, you can write idx times pitch, brackets around, and then dot sum,
Yes.
and then it will be the same. You do not need to fiddle around with all the EDCs, so you can have now also n-dimensional data and everything will work. So brackets, idx
So-
times pitch, yes.
Yes.
Yeah, make brackets around
Yeah.
to really say this is exactly.
So you can also do it like this directly. So you don't have to fiddle around with the size of t and
And that's the reason why pitch dimension -1 is the size of t. That you can do something like that.
so yes. This is how you get the pointer to an element at index idx given the pitches and the pointer to the origin. Obviously, this isn't something you want to write every day and probably something you never want to write. And this is why we suggest that we should use something like MDSpan, which we will cover later. So modern C++ allows us to pass objects which hold both the pitch and the pointer, and then as convenience functions which would do this sort of thing for you. Something I am not covering right now is const correctness. We have a helper above, which can also help you match the constness. So if I get a pointer to a const t, say, I don't want to be able to modify it. Currently, I'm not dealing with this, but it is also possible to pass on the const properties of T across this casting. I will leave it to you as an exercise if you want to do it. Maybe you will learn something. Otherwise, of course, you can see the solution in the next code folder. But for now, I think this is good enough, and we can move back to filling the buffer. So now that I have my get element pointer, all I need to do is use it correctly. So I want to fill in the buffer at point grid thread index y comma x. All I need is get element pointer. Buff data is already my pointer over there. I need the index. This is the grid thread index. And I need the pitches. In bytes, of course, always the pitches are in bytes. This is something we already pass in, and we will show you how to do it soon. But for now, you can assume that the pitches were already passed in. So this is almost it. Y, and that should do it. I have filled in my buffer in parallel because each thread is only filling in the elements it is responsible for. So it's index in the grid, and it is only filling in the corresponding index inside the buffer. There is this implicit one-to-one mapping of the grid to the elements in the buffer. And this is assured by the work division we are passing in. Again, something that you don't need to be concerned about right now, but we will get to it. So, easy as that.
But Tapesh,
Yes?
on the left-hand side, you have an address. And you set this with some value. How can
Excellent. I am really happy that the audience is quite attentive. So, the mistake I made is saying that, hey, give me the pointer to the element whatever, and I'm setting this pointer equal to the analytical solution. What I've forgotten is to dereference it. So now on the left-hand side, I have the actual element being pointed to at index IDX inside buff data.
Sorry, but I don't get, buff data, where does it come from?
So buff data is an alpaca buffer. Mehmet briefly mentioned in his presentation. Maybe I can show it to you. So it's basically a buffer that we define and pass in for you. For the purposes of this exercise, we already created it to be the correct size, and we have passed in this two-dimensional buffer. We will get to it in, I think, the next hands-on session, how you can create your own buffers. But it is basically an alpaca buffer, and when you pass an alpaca buffer to a ACC function, what you need to do is you need to just pass in the pointer it holds. So,
And it's a pitch.
and the pitch, of course, because if you're dealing with pointers, you also need to deal with pitches. Again, this is something that you don't necessarily need to do if you use MDSpan and have modern enough C++. Okay, I will try to compile this. Where is my terminal? Terminal. Found my old one. Okay. So I go into my build folder. I run cmake. ccmake. I activate the serial sequential backend. So another point I want to make is I'm currently activating the HIP backend because I want to use the AMD GPU I get. And I also activate the sequential backend, which will execute this as a serial code. But we also have a bunch of other backends like OpenMP, Threads, TBB, CUDA, SYCL, etc. And one might be tempted to activate, for example, the OpenMP backend to accelerate things on the CPU. This is a good point to make, to know that not all compilers support all sorts of backends. And if I'm using HIP, for the same compiler, I cannot also use OpenMP. This is a compiler limitation, and it is how it is. So if you try to activate this, you will get an error. Just to point it out. Configure. Make, hopefully we have written bug-free code. And let's try to execute. Okay, so over here, we can see the size of our domain, some extra information, the size of a halo. The important part is that the execution results are correct. If you have made an error, maybe you don't get the pointer to the right element, something like this, you might have incorrect results. If you have, this is a good point to check it. So first, this is for the serial backend. Later, for the HIP backend, you see the same thing. Execution results are correct for now.
Why work regions are different for different backends? Good question.
So the question is, why do the work divisions differ for both the backends? So you can see it over here. For the CPU backend, the work division used by Alpaca is 66 by 66 blocks in the grid, and each block has only one thread, and each thread only deals with one element. Whereas on the GPU, we have only 11 blocks in a grid, and each block deals with something like 400. Each block has something like 400 threads, 6 multiplied by 66. And this difference is because obviously on CPUs, each block can only have one thread because of the architectural design of the CPU with only one brain. Whereas on a GPU, you have blocks with a large number of threads. So this is why Alpaca is utilizing different work divisions for different backends. And creating these work divisions is something we get to next. Yes?
Most hardware elements will call an extent, which is currently in 1.1.
This can happen when you define, so the way the work division is defined currently, nothing would trigger thread element extent to be more than one. But sometimes, for example, if you're making your work division manually and you have, some access patterns inside your data might benefit if you look at 4 consecutive elements with the same thread. Then you can take responsibility and say, hey, I will deal with these 4 elements on my own, and you set the thread element extent to 4, and that's all. Then Alpaca will make sure that you jump over the correct number of elements every time. Again, don't worry about work division. We haven't gotten into it in much detail yet, but I think that is the next step. Was everyone able to run this?
Yeah, but I got incorrect results.
Oh no, incorrect results. It's good to hear. will have someone help you debug it. Maybe online? So we have a question in chat. The question asks if we are actually using 64 by 64 threads on the CPU. Obviously, it's not ideal to create a large number of threads. Currently, no. For this serial example, we are only using one CPU thread to run it, but there is another backend, the threads backend, which would spawn a large number of threads and which are then mapped to physical threads. So I'm making the difference between OS threads and physical threads, and then run all of these potentially in parallel, depending on how many threads you have, if you have hyper-threading, stuff like this. Also, if you use the OpenMP backend, which is currently not possible if you also enable the HIP backend, but for the OpenMP backend, it will also use the number of physical cores available on your system on the CPU. Okay. If everyone is okay with this, I suggest we move on to our next presentation.
Should we take a break or?